So we learned a lot in section 9.1. We learned about margin of error, point estimates, z-critical values, what happens to the margin of error and the width of the interval when you increase the confidence level, when you increase your sample size but keep your confidence level the same, how to create a confidence interval, what confidence level is, how to interpret a confidence interval, just tons and tons of stuff. And now in section 9.2, we're going to kind of take those same elements and use them again, but use them for a different parameter. So I don't know if I put this in to your notes back in the day, but if you go back to 9.1, the first page, in 9.1, we're interested in estimating a population parameter P, the true proportion. And I gave a lot of examples, election-based examples. So like what proportion of people are going to vote for, such and such candidate? What proportion of people are going to vote for, this, that, and the other? What proportion of people are going to give away Halloween candy this day? Whatever. So you're trying to estimate the true proportion. You have a statistic P hat, which is X over N, to estimate that. Okay, now we're going to take those same ideas and we're going to use them again, but now we're not going to estimate proportions. We're going to estimate the mean. Let me scroll down to it. There we go. So we're trying to estimate the average. What's the average body temperature? What's the average amount of dollars people spend on Christmas presents this year? What's the average number of trips you take in a lifetime? What's the average number of sick days somebody uses up in 10 years? That kind of stuff. Okay? So how do we figure out those averages? Well, we're going to use the same ideas as before, but we're going to have a little bit of a snag. So let's start off with a point estimate. Now remember, a point estimate is your single best guess. So you have here your losses for a random sample of FBI reported pickpocket offenses. So this is from the FBI data warehouse. You randomly get 25 pickpocket offenses. Here you go. What's your best estimate? Well, you're trying to estimate the average loss in all pickpocket offenses. That's mu, right? You're trying to estimate mu, the average for the population. Well, you don't know the population, but you could get a sample statistic, X bar, and guess from there how it's going to be for all of them. So you need to estimate mu, the average for all offenses. So you're going to go to Excel. And I actually already did this problem and the computer ate my thing, so we'll do it again. But I just called this 9.2 example 1. To be honest with you, I think we're going to use this one several times, the same data set over and over. So it's probably going to end up being more than just example 1, but we'll see. All right, now how do I do this? I just typed equals average A2 to A26. I had the data in there, and there you go. That's our sample average. That's our X bar. So that's our best guess for what mu is. Now, we don't really think it's $513.32. It's not exactly that, but it should be close, right? And then that's what the confidence interval is for you. Confidence interval is how close is close, and what's should? Should is like 95% confident, and then close will be your interval, okay? All right, now before we get into that, though, we have a problem. And it's kind of a big one. We want to make a confidence level, a confidence interval estimate for the average dollar loss of all pickpocket offenses, just like we did before. Like before we were doing, I don't know, the average proportion of red beads in the box or whatever. We learned in section 8.1 that X bar, that average that we're trying to estimate from, X bar has a normal distribution as long as n's bigger than 30, right? With center mu sub X bar equal to mu, right? That's the blank there. So that little box right there, mu. And the spread is sigma over the square root of n. And I just better make a note. As long as n is greater than 30. Oops, 30. Or we know the distribution was normal. Right? Because you have to be told originally that it's normal, or you have to know that n is greater than 30. There we go. I had to fiddle with that font there. All right. So as long as n is greater than 30, or we know the distribution is normal somehow, then we know that the X bar is normal, and we know that it's got center mu and spread sigma over the square root of n. But there's a problem. We can use X bar to estimate mu. No trouble, right? That's not a problem. We did it above, right here. But we want to estimate sigma as well. And we don't have sigma, right? Like if you knew sigma, then you'd know mu, because how are you going to get sigma without mu, right? How do you know the population standard deviation, but you don't know the population mean? It makes no sense, right? So I know what you're thinking. You're thinking, well, Alana, we got away with it back here in 9.1. Yes, well, you get away with it in 9.1 because in 9.1 you're dealing with proportions. And proportions are fundamentally based off of the binomial distribution. I even mentioned it right here. And the binomial distribution, because it's a probability distribution, you basically are like, yeah, I know sigma because it's a probability distribution. Probability means I've got the whole thing covered. I know how the whole population works because it all adds up to 100%. Down here with the mean stuff, we don't have that. So we're kind of in trouble. We don't have sigma. Now, we don't have mu either, but I can use x bar to estimate mu, no problem. But I can't use sigma. And if I can't use sigma, then I'm in trouble because I don't have the normal distribution anymore. Right? I will fundamentally change the shape of the normal distribution, or of the distribution I'm using. Because the normal distribution, that z distribution, that's why we're able to get away with z up in these intervals up here for this formula right here. Do you see that? See the z right there? That's the standard normal distribution. But you only get that if you know sigma. Now, we knew sigma for the proportions, but we don't know sigma down here for the means. We are in trouble. So what they did for years was they kind of just were like, well, they shrugged their shoulders and kind of ignored it. But the problem with that is that it always means that you're always off. In later stats classes, what they'll say is that S is not an unbiased estimator of sigma, right? It's always biased. It's always going to be a little bit off, always. As a matter of fact, we learned the formulas for them way back in the day. Sigma is divided by n, right? Capital N because it's population. And sample standard deviation S is divided by n minus 1. That will mean that n minus 1, because it's a smaller number, will always mean this S is bigger, right? Smaller denominator makes a bigger number overall, right? So not only is S not, you can use it to estimate sigma, but the problem is that when you do that, it's always off. It's always off by a little bit because that denominator is different. Well, how do we get around that? Like I said, back in the day, they just kind of ignored it. Or they would try to figure out a fudge factor, but it was never quite right and whatever. Until a guy who worked for Guinness. Now, Guinness is the brewery in Dublin, the Guinness brewery in Dublin. It's the beer maker that makes stout. It's very popular in Ireland, obviously, and other parts of the world. It's a very nice brew if you're interested in beers and that kind of thing. It's the very, very dark beer. It's called stout. All right, so what Gossett did was he's like, look, I want to be able to take, and we at Guinness want to be able to take small amounts from our vats, small bits of beer, and be able to test them with chemical tests and so on, and see where they're at in the brewing process. Make sure that, okay, the fermentation's really taken hold here. We're ready for the next phase. Or, okay, no, we really need to throw, we're ready for the hops to go in. Or, the alcohol content in this batch is off. He wanted to be able to do that, but from very small amounts, i.e. less than 30, right? But the problem was that before him, it was always off by a little bit because they were using the Z curve, the standard normal curve, and the standard normal curve will never be perfect when you don't know sigma. So what he did was he kind of fiddled around with it, and he came up with a different statistic called the T statistic right here. It's down here. And he figured this out. He got it to work for Guinness. He basically used this statistic rather than the Z statistic to make your confidence intervals. So he'd pull out a little bit and be like, okay, the alcohol content, the average amount of alcohol in this batch is this much, give or take. And he'd be able to make an interval from it. And he was able to make intervals much more accurately than any of their competitors. This gave them a big advantage because they were able to take Guinness was able to take its small samples and do a really good job of monitoring its brewing process, which is better for them as a company. Now, they considered what Gossett had done trade secret because he had done it in their employ. But he considered this so important that he went to his old professor And he said, look, I come up with this thing. You've got to publish this, but we can't publish it under my name because I work for Guinness and it'll, it's a trade secret. And so his professor's like, no problem, no problem. I'll publish it, but we'll use the pen name. I'll send it to the publishers for you. So it's kind of on the sly. And we'll call you student because you're my student. So it's called the student's T distribution, which is what he came up with. So it works a lot like a z-score, but it's not quite the z-score. It's going to look a little bit like the z-distribution, but it's going to have some slightly different properties. And those properties are what allows it to do a better job of estimating from small batches than the z-curve will ever do. Because the z-curve doesn't work well unless n is greater than 30, or it was normal to begin with. So this t thing will work even when we're working with small batches, big batches. It'll work anytime you don't know sigma, which quite frankly, we don't ever get to know. And for a long time, honestly, even into the last few years, people were still using the z distribution even when n was bigger than 30 because they figured, oh, bigger than 30, I'll just use the z. That's becoming less and less in favor now because we have computers that can do the t distribution, Gosset's t distribution so well that it's becoming better to use the t distribution all the time because in real life, you don't know sigma ever. So it's better to use his magical, wonderful, awesome distribution. So let's take a look at the t distribution for just a second and see how it differs from the normal distribution. Now I have here, I made Minitab do this, but basically I took samples of size 5, here's a group of 5, here's a group of 5, and so on. So I have it take 1,500 random samples of size n equals 5 from the z and t distributions, and histograms were drawn of these results, and you're supposed to compare and contrast. So this is the z curve. This is the standard normal distribution. Down here is the t distribution. Now you can see they both have the same center at 0. They're both symmetric, roughly, right? Kind of go up, go down, kind of symmetric around the middle. But the t curve is way more spread out. Look out here at the 4, 5, and 6 stuff. Right? The z doesn't have hardly any, well, nothing you can see at least out there at 4, 5, and 6. So the t curve is way fatter in the tails, more spread out. The t curve also isn't as high. Look at the peak. For the z curve, it's past the 0.4 mark. For the t curve, it doesn't even reach 0.4, not even close. So it's got a shorter peak and fatter tails. That's the t distribution. It's making up for the fact that when you use s, you've got more spread because s has an n-1 in that denominator. It means it's a bigger number. S is always a little bit bigger, so you're always a little bit more spread out when you're working with s than you are with sigma, right? And that's what happens with the t curve. T curve uses s, z curve uses sigma. S is more spread out, so the t curve is more spread out. Now down here, I have 2 different t curves drawn. One when n equals 5, and one when n equals 10. Okay, so you can see when n equals 10, it's taller in the center, right? It gets to the 0.4 mark, which is close to what we were getting with the z curve. But it's still more spread out than the z curve, but it's less spread out than this guy right here. He's got way more in the tails when n is equal to 5 than down here when n is equal to 10. So when n is equal to, when n is equal to 10, it's taller, and when n is equal to 10, it has smaller tails, right? Less spread, smaller tails than when n is equal to 5. And now you've learned another lesson about the t curve, which is that there's lots of them, right? There's tons and tons and tons of them, infinitely many, in fact. They're based on something called degrees of freedom, which is equal to n-1. Where does the n-1 come from? Well, it comes from a lot of things that I don't want to get too deep into, but suffice it to say that because it's based on s, the t curve is based on s, and the denominator of s is n-1, that's sort of where it's coming from in the formula. But what it means is that the first n-1 things are free to be whatever they want in the data set, but that nth one, that last one, has no freedom. It has to be whatever it takes to make the sum of the deviations equal to 0. All right, that's where we'll pick up next time with this degrees of freedom stuff. I'll see you then.